Hello everyone, welcome to this lecture on applications of derivative and today we are going to talk about monotonic functions and what is concavity. So we are already doing the applications of derivatives, okay, and today we are going to talk about these two applications, that how we can utilize derivatives of a function to see whether the function is monotonic or not. By monotonic we mean that whether it is increasing or decreasing on an interval, okay, and also how to check using derivatives the concavity. Okay, so concavity, by concavity we mean the bends or turns in the graph. Okay, so first we will talk about the uh, monotonic or monotonicity of a function. So we'll talk about the increasing or decreasing of a function. Okay, so first we take this definition about increasing functions and decreasing functions in an interval. So let f be a function defined on an interval I, and let x1 and x2 be any 2 points in this interval I. Okay, then uh, if x1 lies to the left of x2, okay, then uh, for all such x1 which lies to the left of x2 in that interval, if the corresponding function value of x1 is less than the function value of x2, then we say that function is increasing. Okay, so as we move from left to right, okay, the corresponding function value becomes greater than the function value of previous points, then we say that function is increasing. Okay, and similarly for all x2 points greater than x1, okay, if the function value at x2 is less than fx1, then we say that function is decreasing on the interval. Okay, so for example, if we talk about this curve y is equal to x, and if I take any 2 points, say x1 and x2, then the corresponding functions values fx1 and fx2. Okay, so if x2 is greater than x1, the corresponding function value at x2 is greater than fx1, then we say that function is increasing in that interval, if this is true for every pair of points x1 x2 of the interval in which the function is defined. Similarly, if I take any 2 points, say x1 x2 here, and the corresponding function value are fx1 and fx2, so for all x2 greater than x1, if fx2 is less than fx1, then we say that function is decreasing. Okay, so here are two examples that this function is increasing for all x in the domain of the function, and this function is decreasing for all x on the left side of origin, and increasing for all x on the right side of the origin. So that means uh, we can if we divide the domain into sub intervals, then in certain sub intervals the function will be decreasing, and in some sub intervals the function will be increasing. Okay, so in that sub interval we can say that the function is monotonic. Okay, so now this how we can check this with the help of derivative, that in which interval the function is decreasing and in which interval the uh, function is increasing. Okay, so in fact if you look at the derivative, that means slopes of the curve, then that gives us the nature of the function, whether it is increasing or decreasing. So in this case we said function is always increasing, so you can see that the slope at every point is positive. Okay, and in this case the function is decreasing to the left of origin, and you can see that at any point if you draw the slope, then the slope is negative, and on the right of origin, if you do the slope at any point, and you see that the slope is positive. Okay, so if the first derivative is negative for in an interval, then the function is decreasing in that interval, and if the first derivative is positive in an interval, then the function is increasing in that interval. So this is exactly what our first result says, and it's a corollary because it's an immediate consequence of the mean value theorem. And it says that suppose that f is continuous on a closed interval ab and differentiable on open interval ab, then if the first derivative x is positive for every point x in this open interval ab, then function is increasing on the closed interval ab. Okay, and also if the first derivative is negative, that means the slope is negative at each point in the interval, then the function is decreasing on that interval. So we are going to prove this result. Okay, and as I said, that it is a consequence of mean value theorem. It satisfies all the properties hypothesis of mean value theorem. Okay, that the function is continuous on AB and it is differentiable in open interval AB. So let x1 and x2 be any 2 points in this interval AB with the x1 less than x2. So x2 lies to the right of x1. So and then for this interval x1 and x2, the mean value theorem will be satisfied because function is continuous in AB and differentiable in open AB, and x1 and x2 are any 2 points in AB. So for the interval x1 x2, the function is continuous in this and function is differentiable in the open interval. So we can apply mean value theorem, and which says that there exists a point C between the interval x1 x2 such that the slope at C is uh, equal to the slope of secant. Okay, so fx2 minus fx1 by x2 minus x1 is f dash c for some c between x1 and x2, which is rewritten here by taking denominator to other side. Okay, now the right hand side, because x2 lies to the right of x1, so x2 minus x1 is always positive. Okay, so the sign of left hand side only depends on the sign of the derivative at c. Okay, so if the slope is positive at c, okay, so then this right hand side will become positive. If slope is negative at c, then this right hand side will become negative. So and accordingly the sign of the left hand side will occur, and so we will have our result. Okay, so the sign of right hand side of this equation is same as the sign of f dash c, because x2 minus x1 is positive. That's exactly what I said. And so if the slope is positive, if f dash c is positive on the interval, then fx2 will be greater than fx1. Okay, and that means whenever x2 is greater than x1, fx2 is greater than fx1, means the function is increasing function. Okay, so that's exactly what is we prove this first statement. Okay, that the function is increasing if derivative is positive. Similarly, if derivative is negative, then this right hand side is negative, which implies that fx2 will be less than fx1. Okay, and so for x2 greater than x1, if fx2 is less than fx1, then the function is decreasing. Okay, so when derivative is negative, the function is decreasing on AB. Okay, so that proves our first result, that we can check if the function is increasing or decreasing by calculating the uh, slope of the function in that interval. Okay, uh, now how to find the intervals on which we have to check whether the function is increasing or decreasing. We said that we can check whether it is increasing or decreasing by calculating the slope at a point inside that interval. But if you are given a domain, say all R, then how we can construct those intervals where function will be increasing or decreasing. Okay, so for that we calculate the critical points of the function, and as I said in the previous lecture, that critical points are those points in the interior of the domain where either the first derivative is 0 or the first derivative do not exist. Okay, so to find the critical points of the function, what you have to do is you have to calculate the first derivative of the function. Okay, and then you have to check, or you have to find all those points of the domain at which that first derivative is either 0 or at which the first derivative is not defined. Okay, so all those points which are points of domain will become then critical points. Okay, and then those critical points will divide the domain into subintervals. Okay, so if you have two critical points, say a and b, with a less than b, okay, and there is no other critical point between this. Okay, that means if the derivative of function is continuous but never 0 on this interval, okay, the derivative must be everywhere positive on ab or everywhere negative here. Okay, so if there is no critical point inside this, then in this interval, if I calculate, if I take any point between a and b, then the derivative will be either positive, okay, or negative, and that will be true for every point in this interval. Okay, so you just need to take any one point between a and b and check what is the sign of the derivative. If it is positive, then it will be positive for every point between a and b. If it is negative, then it will be negative for every point between a and b. Okay, okay, so this is the method that you calculate the critical points that will divide the domain into subintervals, and then for each subinterval you can check the sign of derivative by simply taking any point inside that interval. Okay, and then check the derivative at that point. If it is positive, okay, the function is increasing in that interval. If it is negative, then the function is decreasing in that interval. Okay, so f dash c positive, then that means that the slope is positive for every x in this interval. Okay, so function is increasing by the corollary. And if derivative at c is negative, then derivative is negative for every x in AB, and so function will be decreasing in AB. Okay, so where A and B are critical points. Okay, and there is no critical point between A and B. Okay, say for example, find the critical points of the function this x cube minus 12x minus 5, and identify the open intervals on which the function is increasing and on which the function is decreasing. So first we note that the right hand side is cubic polynomial, and the domain of this is complete R. Okay, so domain is R. Then to find or divide that domain into subintervals where we can see where it is increasing or decreasing, what we need to do is find its first derivative. Okay, so calculate df by dx, okay, which will be 3x square minus 12. Okay, so calculate the first derivative. Okay, and then find out the critical points. Okay, that means where the derivative is 0 or where the derivative is undefined. Okay, the domain of derivative is again complete R. Okay, so there is no point x where the derivative is undefined. Okay, so only points are where derivative becomes 0. Okay, which is x is equal to minus 2 or x is equal to plus 2. Okay, so x is equal to minus 2 and plus 2 are the only critical points. Okay, and there are no endpoints for this. Okay, so we just need to divide the domain R into intervals from minus infinity up to minus 2, then minus 2 to 2, and then 2 to infinity. Okay, so the domain is divided into three intervals. Okay, which are non-overlapping open intervals: minus infinity to minus 2, minus 2 to 2, and 2 to infinity, just because the critical points are these two, minus 2 and 2. Okay, so now for each interval we just need to check the sign of the derivative at any one point inside this interval. Okay, so if the sign is positive, then it will remain positive for all other x points inside. Okay, similarly for the second interval and similarly for the third interval, and whenever the sign will be positive, the function will be increasing in that interval, and whenever the sign is negative, the function will be decreasing in that interval. Okay, so uh, these were the derivative and critical points. Okay, so now we have three intervals and we have to evaluate the derivative at any point inside that interval and see what is the sign of the derivative, positive or negative, and the sign will tell whether the function is increasing in that interval or decreasing. Okay, say for example the first interval is minus infinity to minus 2, so you choose any point inside this. Say I chose x to be minus 3, which lies in this interval, and calculated the derivative at minus 3. So you can calculate the value and say it is 15 here. Okay, so the value is positive, and if value is positive, that means that the function is increasing in this interval minus infinity to minus 2. Okay, so for all x lying in minus infinity to minus 2, the function behavior is increasing function. Okay, then the second interval is minus 2 to 2. Okay, so you choose any point between minus 2 and 2. You choose minus 1, 1, 0, or you choose points in decimal, half, minus half. Okay, choose any one point. Okay, say I took 0, which is easy to evaluate. Okay, so this will give minus 12 value. It is negative sign, so the function behavior is that it is decreasing for every point x in this interval. And the third interval was 2 to infinity, so you pick any point between 2 and infinity, evaluate the derivative. Okay, here it is positive again. Okay, and so function behavior is that it is increasing in this interval 2 to infinity. Okay, so this way we can check whether the function is increasing or decreasing uh, in a interval. Okay, so your domain was this. Okay, the complete real, and you calculated two critical points, minus 2 and 2. Okay, so this point and this point. Okay, and so for all minus infinity to minus 2, what we found is that the function is increasing. Okay, so minus infinity to minus 2, function is increasing. Okay, then from minus 2 to 2, okay, we found that function is decreasing. Okay, minus 2 to 2, the function is decreasing, and then after 2 to infinity, the function again increases. Okay, so the graph also tells us the same situation, that from up to minus 2 it is increasing, then it decreases up to domain value 2, and then it starts increasing as x rises from 2 to infinity. Okay, so this was one example. Okay, so the second result is the first derivative test for the local extremas. Local extrema means the local maxima or the local minima. Okay, then so how we can now utilize the derivative, okay, the first derivative, to find the points of local maxima or local minima. Okay, so suppose that C is a critical point of a continuous function f. Okay, and that f is differentiable at every point in some interval containing C, except possibly at C itself. Okay, so if you have a critical point and function has derivative in some interval containing this C. Okay, so if a to b is interval such that C lies inside, and the function is differentiable at every point except possibly at C where it may not have a derivative. Okay, then moving across the interval from left to right, as we move from the left side to right side, this holds. Okay, that if the derivative changes from negative to positive at C, then function has a local minima at C. Okay, so uh, we just said that when the derivative is negative, that means the function is decreasing in the interval. Okay, and if the derivative is positive, then the function is increasing in that interval. So if derivative changes sign from negative to positive, means the function was decreasing, and then after C it starts increasing, then you see that as I move left to right, it decreases and then increases. So this point C, okay, it becomes a point of local minima. Okay, okay, so this function has a local minima at C. Similarly, if the derivative changes from positive to negative, okay, so that means the function increases and then decreases. Then at C there is a local maxima. Okay, and if derivative does not change sign at C, okay, that means the derivative is positive on both sides of C or negative on both sides of C, then function has no local extrema at C. Okay, so if the function is increasing and then after C it's remain increasing, then there is no then that point C cannot be a maxima, nor it can be a minima. Okay, similarly if was decreasing till C and then further decreasing, then this point cannot be a minima or maxima. Okay, say for example, if you have this blue curve, okay, as a function, then the critical points of C, this function will be those points where either the slope is 0, okay, or the points where derivative do not exist, like corner points or cusp, okay, or vertical tangent. So let's say this C1 point where slope is 0, or C2 point where slope is 0, or C3 point where slope is 0, or C4 point where derivative do not exist, or C5 where slope is 0. Okay, so these are the critical points, and then also there are some endpoints. Okay, so the first says that if derivative changes from negative to positive, then it has a local minima. Okay, like this is the point, say the slope on the left of this point is negative and the slope on the right of this is positive. Okay, so slope changes sign from negative to positive, so this becomes a point of local minima. Okay, C3. Okay, and the corresponding value is a local minimum value. Similarly, say this point, the derivative here is 0, so this point is a critical point C2. Okay, so if we see the derivative sign on the left and right, okay, so the derivative sign on the left is positive, okay, the slope on this side is positive and the slope on this side is negative. Okay, so as we move from this side to this side, the slope positive changes to slope negative. Okay, so this is a point of local maxima, this statement. Okay, and the third statement says that if sign do not change, like in C1 point there is a critical point here, but on the left side slope is positive, okay, and on the right side also slope is positive. So the sign of slope do not change, then this point cannot be an extremum. There is no maxima or minima at this point. Okay, so to find local maxima or local minima, you can also check the behavior, how the first derivative sign changes to the left or right of that point. Okay, also uh, at the end points also we can use this result. Okay, but that will be one sided. Okay, so if to the right side of the end point, if slope is positive, then it is a minima. If slope is negative, then it's a local maxima. And if to the left of the upper end point, if the slope is negative, then it is minima. If slope is positive, then it is a local maxima. Okay, and then in the last lecture also I said that if you have some local maximum points, then you can compare them to find the absolute maxima, and if you have some local minimum points calculated, then you can compare those local minimas to find the absolute minima. Okay, so now take say example to uh, find the critical points of this function. Okay, so you can easily see that the domain of this is the R, and identify all the open intervals on which function is increasing or decreasing. Okay, and find the function's local and absolute extreme values. Okay, So to find the critical points, first what we have to do is take first derivative of this function with respect to x. Okay, so we can calculate the first derivative by product rule: first function derivative second plus second function derivative first. Okay, and then you can recombine them, you will get this value. Okay, now the critical points will be those points of the domain at which uh, either the derivative is 0 or undefined. Okay, so here x is equal to 1 is a point where derivative which will make this derivative 0. Okay, so x is equal to 1 is a critical point, and also x is equal to 0 is a point which will make this derivative undefined. Okay, so x is equal to 0 is also a critical point. Okay, so basically the domain can be divided into subintervals minus infinity to 0, then 0 to 1, and 1 to infinity. Okay, and in these subintervals either the function will be increasing or decreasing. Okay, right. So let us check the points where the function is increasing or decreasing first. Okay, so for minus infinity to 0, that means for all x less than 0, we have to check what is the sign of derivative. So take any point less than 0. Okay, and put that x value here and see what is the sign of derivative. Say if you choose -1 or -2 or -3, any point of value of x. Okay, so whenever x will be less than 0, that means negative, this quantity x minus 1 will be negative. Okay, and this quantity will be positive, so the product will be negative. So the slope of function will be negative, or sign of f dash will be negative. So behavior of the function is that function is decreasing in minus infinity to 0. Okay, then second interval is 0 to 1, so you choose any value between 0 and 1. So you see that if I choose anything x as between 0 and 1, this difference will be negative, and this will be positive number, so product is again negative. Okay, so we will get a negative sign of f dash, and if it is a negative sign, then function is decreasing in this interval also. Then the interval is from 1 to infinity. When x is greater than 1, then this difference will be positive, this number is positive, so product will be positive. Okay, so slope sign will be positive and the behavior will be increasing. Okay, so easy to calculate the function behavior by using the sign of the derivative. Okay, okay, so the first derivative test. Okay, what does it say? It says that if the sign of the derivative changes from negative to positive or positive to negative. Okay, as we move from the left to right and pass through the critical point, then we have a maxima or minima, local maxima or minima there. Okay, so you can easily see here that the sign is negative for x less than 0 and sign is negative for x greater than 0. Okay, so sign do not change as we move from the left to right. Okay, so there is no maxima or minima at x equal to 0, so it does not have any extreme value at x0. Okay, f dash do not change sign, and the slope was negative, and then it becomes positive as we cross the point 1. Okay, x is equal to 1. Okay, so when slope is negative and then it becomes positive, that means there is a local minima at that point. Okay, so x is equal to 1 is a point of local minima. Okay, and you can calculate the value of local minima by using x is equal to 1 in the function. Okay, so that point. So this point, or this is also the absolute minima. Okay, because the function is decreasing for all x before x is equal to 1 and increasing for all x greater than 1. Okay, so if you simply plot this, then for minus infinity to 0 it was decreasing, and then for 0 to 1 it was further decreasing, and then it starts increasing for x greater than 1. Okay, so this is the point of local minima, and at x is equal to 0 there is neither maxima nor minima. Okay, further you can see that as x approaches 0, the derivative tends to minus infinity. Okay, so if you approach x 0 from negative side or positive side, what happens to this slope value? Okay, so that you can easily check, or you can also check using the method that we discussed in the previous lecture. Okay, about slopes of function. Okay, so you can take this point as p and then take a neighborhood point q here, so slope is negative. Okay, and then when q moves towards p, the negative slope becomes vertical, so that means left hand derivative is minus infinity. And if you choose point p here and q on the right side, and then so again there is a secant slope is negative, and if you move this q point towards p, then this negative slope becomes vertical, so that means the right hand derivative value is also minus infinity. And we know if left and right and derivative are both minus infinity or plus infinity, then at that point we have a vertical tangent. Okay, so this we have already talked about this in previous lecture. Okay, so next is the concavity. That means uh, how the graph of a differentiable function bends or it turns. Okay, so second derivative tells us about this. Okay, the turning and bending behavior of the curve or graph is defines the concavity. Okay, so either the graph can be concave up or concave down. Okay, depending uh, upon the function. Okay, behavior. So so let us first define this, that the graph of a differentiable function y is equal to fx is said to be concave up on an open interval I if first derivative is increasing on I. Okay, and it is said to be concave down on an open interval I if first derivative is decreasing on that interval. Okay, so for example, if you have a curve y is equal to x cube, then uh, from left to right as x values move, what happens to the slope? Okay, and so first derivative, you see that here the first derivative is this, and as we move on this blue curve toward right, the slope started to bend or decrease. Okay, and the slope is positive, and slope is still positive, but its value is decreased. Okay, so if slope is decreasing, then we say that the graph is concave down. So this graph is concave down. Okay, on the right side, if you see that at this point the slope is here. Okay, and as you move towards right, the slope becomes here. Okay, so the slope is increasing. Okay, so if slope is increasing, then we say that concave up. Okay, so this part of graph is concave up. Okay, and say for example y is equal to x square curve. So if you calculate the slope on this left side, okay, the slope here at this point will be a negative slope, and then again negative, then again negative. But as we move on this negative slope value is decreasing. Okay, so that means slope is actually increasing. Okay, so if the slope is increasing, then it is concave up, and similarly the slope on this side is also increasing. So positive value is increasing for slope, so it is again concave up. Okay, okay. So concavity, very simply the bend or turn in the graph which can be concave up or concave down depending upon the behavior of the slope or tangent on the interval. So as we move from left to right, what happens to the tangent values? Okay, if slope starts decreasing, then it is concave down. If slope starts increasing, and then it is concave up. Okay, now the idea is that uh, if how we can utilize the derivatives to check this concavity. Okay, and the second derivative is very important here, which tells us about the concavity of curves. Okay, so the second derivative test for concavity, that let y is equal to fx be twice differentiable on an interval I, and if the second derivative is positive on the interval, then the function is concave up over that interval. Okay, and if the second derivative is negative on an interval, then the function is concave down in that interval. Okay, so a function is differentiable, twice differentiable in interval, then you can check whether the second derivative is positive in that interval or second derivative is negative in that interval, and that will tell us whether it is concave up or concave down. Okay, so if you remember that the result we did today, that if a function is increasing, then its first derivative is positive. Okay, and if we use that result here, then second derivative positive means that the first derivative is increasing. Okay, and on the previous slide we just saw that if first derivative is increasing, then it is concave up. Okay, so the proof is very simple here. Okay, the second derivative positive in interval simply means that the first derivative is increasing on this interval, and which by definition says that it is concave up. Okay, and second derivative negative in interval means that this first derivative is decreasing on this interval, which means that the function is concave down. Okay, by definition. So for example, now we can check this mathematically, that if you have a y is equal to x cube curve, then if we calculate the second derivative of this, so that will be 6 times x, that means a twice differentiable function. And then this 6 times x value is negative for x less than 0, and it is positive for x greater than 0. That means second derivative is negative for all x less than 0, and second derivative is positive for all x greater than 0. So that means it is concave down in for x less than 0 and concave up for x greater than 0. That's exactly what we see from here, that it's concave down for x less than 0 and concave up for x greater than 0. Okay, and say the other function y is equal to x square parabola, the curve this has second derivative as 2. Okay, the first derivative is 2x and second derivative is 2, and this value is always positive for all x. Okay, in the domain. So if you choose x negative or positive, second derivative is always positive. So that means if second derivative is positive, it is always concave up. So that's why this curve is always concave up. Okay, so this test is important. Okay, because we can easily check the concavity of functions by calculating the sign of second derivative of the function. Okay, say for example, determine the concavity of y is equal to 3 plus sin x on closed interval 0 to 2 pi. Okay, so to check concavity, we can calculate the second derivative of this. Okay, so y first derivative, okay, sin x is cos sin x, and the second derivative of this is minus of sin x. Okay, so now you can check on this interval where the second derivative is negative and where the second derivative is positive. Okay, so you can see that for all x in 0 to pi, the second derivative is negative. That means in 0 to pi the function is concave down, and in pi to 2 pi the second derivative becomes positive, because sine of theta for all theta in this will be negative, so it becomes positive. And so the function 3 plus sin x will be concave up in pi to 2 pi. Okay, so here's the plot of 3 plus sin x, and you can see that for x value 0 to pi it is concave down. Okay, so if you calculate slopes here, okay, as you move from here to here, you can see that slope was positive, then decreasing, positive but decreasing, it becomes 0, and then start becoming negative. Okay, and on this side it is concave up, and from pi to 2 pi, and you can see that slope is negative, but negative slope starts decreasing and becomes 0, so slope is actually increasing and then further increasing on this side. Okay, so it is concave up. Okay, so you can also see that we have plotted a second derivative function minus sine x here, which tells that in between 0 and pi the second derivative values are negative below the axis, and in pi to 2 pi the second derivative values are positive above the axis. Okay, so the second derivative is negative for all x in 0 to pi and positive for all x in pi to 2 pi. Okay, now there is an interesting point shown here. X is equal to pi, the corresponding value is pi 3, and here we have a tangent and this curve crosses this tangent here. Okay, so we'll talk about this point, and this such points are called uh, the points of inflection. Okay, because the concavity on the one side of this is concave down and concavity on the other side of this is concave up. Okay, so the tangent exists here. Okay, there is a tangent here in this point and the concavity is changing sign, so such points are called the points of inflection. So I just give you the definition of this, that the points of inflection and a point C f of C, okay, where the graph of a function has a tangent line and where the concavity changes is a point of inflection. Okay, so there are two things here, that the graph should have a tangent line there. Okay, and the other, that the concavity sign should change. Okay, if it is concave down then concave up, or from concave up to concave down. Okay, so concavity if changes and there is a tangent line there, then this point becomes the point of inflection. Okay, so it is easy to note here that at the point of inflection either the second derivative is 0 or the second derivative will fail to exist. Okay, and the converse may not be true. Okay, so if you calculate second derivative and if you found some point x on which the second derivative is 0 or second derivative fails to exist, that does not mean that it is a point of inflection. We must see the change in concavity also. So uh, uh, okay, so one must check for the change in concavity. Okay, so concavity must change from concave down to concave up or concave up to concave down at such points, and then only we can say that those points are points of inflection. Okay, so this also gives us an idea to how we can check points of inflection. Okay, that if we calculate the second derivative of function and if we put second derivative equal to 0 and calculate the points, and also note all the points where second derivative failed to exist, and at those points if we check how the concavity is behaving in an open interval containing that point. So if the concavity is changing, then we can say those points are point of inflection, otherwise those points are not point of inflection. Okay, say for example the graph of function f(x) equal to x raised power 5 by 3. Okay, it has a horizontal tangent at origin. Okay, because you can see that first derivative of this is 0 at x is equal to 0. So at x is equal to 0, slope is 0, so there is a horizontal tangent here. Okay, and if you calculate the second derivative of this function, then this second derivative is 10 by 9 x raised to a minus 1 by 3. So x is equal to 0, uh, at x is equal to 0 the second derivative fails to exist. Okay, so at x is equal to 0 we can have inflection point if the concavity changes as point on the domain move from left to right passing through origin. Okay, so if I check the concavity for on the both side of origin, that means for x less than 0 what are the values here, and for x positive what are the values here. Okay, so the second derivative sign is negative for x less than 0 and second derivative sign is positive for x greater than 0. So concavity is changing. Okay, and so the point x is equal to 0 is a point of inflection at origin. Okay, so this way you can easily check. Okay, okay, so there's on the left side of this there is a concave down, on the right side of this there is a concave up, and at this point there is a tangent, okay, which is a horizontal tangent. Okay, so tangent exists and concavity changing, so this point is a point of inflection. Okay, okay, so there's another example which says that this curve has no point of inflection at origin. Okay, even though you can see easily that if you calculate the first derivative, second derivative, then at second derivative is 0 at origin. Okay, so slope is okay, and first derivative is also 0 at origin, so it also has a horizontal tangent at origin. Okay, but the uh, point is not a point of inflection because the concavity do not change in this case, so you can easily check this that the uh, second derivative, okay, which is 12x here, is always positive for all x. If you choose x less than 0 points or x greater than 0 points, the second derivative remains always positive. Okay, so there is concavity do not change uh, as we on the left of origin or to the right of origin. Okay, even though their first derivative at origin is 0, that means there is a tangent there, okay, horizontal tangent, but this point is not a point of inflection because the concavity do not change. Okay, so this is the graph. Okay, so it is concave up on the left and it is also concave up on the right. Okay, so this point is not a point of inflection. Okay, now we talk about the second derivative test for the local extreme values, that means local maxima or local minima. Suppose second derivative is continuous on an interval that contains x is equal to c point, and if the first derivative at c is 0 and second derivative at c is negative, then the function has a local maximum at x is equal to c. Okay, so here the second derivative continuity is important because if second derivative is negative at this point and the second derivative is continuous, that means the second derivative will be negative for all x points in the neighborhood of point C. Okay, so in the interval A to B containing the point C. Okay, and if the second derivative is negative in the interval containing C, then that means uh, that the function or is concave down in that interval, or you can say that the first derivative is decreasing in that interval, and because the first derivative is 0 at c, and so in that interval derivative will decrease only if the slope will change from positive to 0 to negative. Okay, and that is only possible when you have a local maxima at x is equal to c. Okay, so if also if derivative is 0 at c and second derivative is positive at c, then f has a local minima at x is equal to c. So again with the similar argument that if second derivative is positive at c and second derivative is continuous in open interval containing c, then for all x in this open interval the second derivative will be positive, and that means the first derivative will be increasing, and if first derivative is increasing such that the first derivative at c is 0, then in that interval that means that the slope was negative which becomes 0 and which become positive as we move from left to right in the interval. Okay, so that immediately says that it has a local minima. Okay, and if both first derivative and second derivative are exactly 0 at the point c, then this test fails, okay, and the function may have a local maxima or minima, or it may not have anything at that point, okay. So we'll give a counter example to prove this, okay. So first, the proof of first part, as I said, that if second derivative is negative at C, and because second derivative is continuous in the open interval containing C, so that means uh, second derivative at all x points should be negative for all x in that open interval, okay. And this immediately means that the first derivative should be decreasing on that interval, and because the derivative at C is 0 and C is a point in this interval, so this is only possible if you had a positive slope which becomes 0 slope and then become negative slope. So there is a point of local maxima, okay. So the derivative is actually changing sign from positive to negative, and so we have a local maxima by the first derivative test, okay. So these two conditions if satisfied and second derivative continuous, then we have a local maxima there, okay. The second part can be proved similarly, okay. So I'm leaving that proof, so you can use the similar argument to prove this, okay. For the third part, we have a counter example that there are functions which satisfies both conditions, and uh, for one function there is a local maxima, for other there is a minima, and for third there is a neither a maxima or a minima, okay. So for example, the function y is equal to x power 4, y is equal to minus x power 4, and y is equal to x cube. So all these functions, if you calculate the first and second derivative, and you can see that at origin x is equal to 0, both the first and second derivatives are exactly 0, okay. So that's the condition 3, okay. But this function second derivative is 12x square, okay, and which is always positive for all x to the left of origin or right of origin. So that means it is always concave up, so it has a point of local minima, okay, uh, right. And similarly this function, it is always second derivative is always negative, okay, for all x to the left or right, okay. So it is always concave down, and so it has a point of local maxima at x is equal to 0, okay. And similarly y is equal to x cube, okay. So it does not have a local maxima or local minima at x is equal to 0, okay. The concavity is changing, so it is a point of inflection, okay. So this shows that the test will fail if you have both first and second derivative exactly 0 at x is equal to c, okay. C in this case is particularly 0, okay. Right. So now we take one last example for today, that for the function fx is equal to x power 4 minus 4x cube plus 10, identify where the extrema of functions occur, okay. So find out where the function has local maxima, minima, okay. Find the intervals on which function is increasing and intervals on which function is decreasing. Find where the graph of function is concave up and where it is concave down, okay. So to first we should note that the domain of this function is R, okay, and then we calculate the first derivative of this function and the second derivative of this function, okay. So given this function and domain is R minus infinity to plus infinity, the first derivative of this function is 4x cube minus 12x square, and domain of this function is again R, okay. And the second derivative is 12x square minus 24x, and again the domain is R, okay. So to find the intervals where you have function increasing or decreasing, we first note what are the critical points of the function, okay, by finding those x values where first derivative either is 0 or it do not exist, okay. So that second case is not there because domain of this is R, okay. So only the points will be the points where first derivative is 0, okay. And those critical points are x is equal to 0 and x is equal to 3, so we can solve this equal to 0 to find these 2 points. Okay, so it will divide the domain into uh, sub intervals minus infinity to 0, 0 to 3 and 3 to infinity, and on these intervals we can check whether function is increasing or decreasing. Okay, so first interval is when x is less than 0, that means minus infinity to 0. Okay, so we can see the sign of derivative by using any x value in this interval. Say x is equal to -1 if we use and substitute it here, so you can see that the sign of derivative is negative, so that means that the function is decreasing in that interval. Okay, similarly the second interval is 0 to 3, so you can choose any x values between 0 and 3, say 1 or 2 or maybe in decimals, and see what is the sign of this function. Okay, so for x value between 0 and 3, this will be negative. Okay, so again the function is decreasing. And then for all x greater than 3, so up to 3 to infinity, so if we choose x as 4, 5 or any number, okay, and check the sign of the derivative, so you can see and check that it is positive, that means function is increasing in this interval 3 to infinity. Okay, now there are few points you can note here, that the derivative change sign at x is equal to 3 and derivative do not change sign at x is equal to 0. Okay, so at x is equal to 0 there is no local maxima or minima because there is no change in sign, and because the derivative change from negative to positive, or the function behavior is decreasing to increasing. Okay, then so it has a local minima at x is equal to 3. Okay, and further the function is decreasing and decreasing for up to 3, and then it is increasing for x greater than 3. Okay, now we will check the concavity, and for concavity we have to use the uh, those points where either second derivative is 0 or second derivative do not exist. Okay, so second derivative exists for all points in R. The only points where concavity will change will be or the points will be where second derivative is 0. Okay, which will divide the intervals of the domain. Okay, so second derivative is equal to 0 when x is 0 or x is 2. Okay, so this also divides the domain into intervals minus infinity to 0, then 0 to 2, and then 2 to infinity. Okay, so for all x less than 0, uh, we see the sign of second derivative, so you choose any point x less than 0 and put in this second derivative. Okay, and see what sign is there. Okay, so for example x is -1, so we get 12 plus 24 which is 36, so we get positive value. Okay, so behavior of function is that it is concave up for all x less than 0. Okay, for all x between 0 and 2, you choose any point, say x1, and see that difference will be negative, so it is concave down in 0 to 2. Okay, and then for all x greater than 2, so you use any point or any value of x greater than 2 here and see what is the sign of second derivative. Okay, so if it is positive, so it is concave up for all x greater than 2. Okay, so we can combine the two results. Okay, uh, the intervals have to be carefully written because the intervals were x less than 0, then we had 0 to 2, then okay, here it is I wrote it wrong, it is 2 to 3. Okay, 2 to 3. Okay, and then greater than 3, so this value is 2 here. Okay, so x less than 0, then 0 to 2, then 2 to 3, and then greater than 3. Okay, so because uh, 0 and 3 were critical points, and 0 and 2 are the points by second derivative. Okay, so all x less than 0 is one interval, then 0 to 2 is second interval, then we have interval 2 to 3. Okay, by previous slide, and then 3 greater for all x greater than 3. Okay, and then we can note the behavior. Okay, for up to 3 we had decreasing function, and for x greater than 3 we had increasing, and from here uh, up to 0 we have concave up, then 0 to 2 we have concave down, and for all x greater than 2 we have concave up. So for 2 to 3, okay, this is 2, remember, 2 to 3 it is concave up, and x greater than 3 it is concave up. Okay, so you can check this through the graph also. Okay, that this is the function graph. Okay, and for all x less than 0, okay, the function is decreasing and concave up. Okay, uh, for 0 uh, up to 2, okay, the graph is decreasing and concave down. Okay, so it is decreasing and concave down, and then from 2 to 3 it is decreasing and concave up. Okay, so it becomes decreasing and concave up. Okay, and for 3 greater it is increasing and concave up. Okay, so it is concave up and increasing. So where do the concavity is changing? Okay, it is changing at x0, and it is changing at x is equal to 2. Okay, so at x is equal to 0 and x is equal to 2, okay, concavity is changing, and the tangents exist. You can check the first derivative values at x0 and x2. Okay, so tangents are there. Okay, so these 2 points are points of inflection. Okay, uh, the function changes decreasing to increasing. Okay, at x is equal to 3, so it's a point of local minima. Okay, so all these things you can check, and then we can utilize these important properties uh, to graph the function. Okay, and that will be our next lecture. Okay, the curve sketching. Okay, so what important properties we can check from function and how we can sketch the curve, and then we will talk about indeterminate forms and how to find the values of indeterminate forms by L'Hopital rule. Okay, so that's it for today. Have a very good day.